Good day, Year 12. Welcome to Differential Equations, a brand new topic in the Extension 1 syllabus. This will be 2 videos because it's a long lesson, 5 pages of notes and questions. And the first one will stop when you're able to then go on and do some of the exercise. And then the second one will do further questions and other things and give a broader introduction to the topic. So in this lesson, we'll be learning what a differential equation is. We'll be seeing how our existing skills apply because it is just calculus. And the key focus today is how to solve differential equations of this form, which will make sense in a minute. We're going to learn what kinds of differential equations we're solving in this topic and how differential equations are classified. That'll definitely be in the second video. And see some examples of differential equations that apply to science. They're extremely important. There would really be no modern science without differential equations or engineering. Okay, so exercise 1. Is just a little description of what you'll get when you look at the exercise 1. But you'll be applying the general skills that you learn in this lesson and solving equations of this form. Okay, let's get into it. So the first question is to solve 3x squared plus 1 equals 17. A very simple question, but it's here for a reason. So we have 3x squared equals 16, and x squared is 16 over 3. X equals plus or minus 4 over root 3. We could rationalise, but that's not the point here. The point is we had a pretty simple equation to solve, and our answer was a number. And that's what we kind of expect. When we solve an equation, we expect to get a number. And if we look at this aside here, then we've got a trig equation here. If you solve that, you'll get a number. There are infinitely many solutions to that equation. This one, you'll get a number. A will be somewhere between 0 and 1. So only one solution in the real numbers. And here, y dash equals 1 plus y squared. Well, that's an equation, but it's a different kind of equation. Spoiler alert, it's a differential equation. What we can see here is that y cannot be a number in this number sentence, in this equation. If y was equal to 5, say, then on the right-hand side you'd have 26, and on the left-hand side you'd have 5 dash. But the problem is 5 dash doesn't mean anything. So y can't be a number. What can you put a dash in? A function. Y has to be a function for this to work. So differential equations are equations that have a function as an answer. The equation involves derivatives of that function. Okay, so let's get on with it. Solve dy dx equals sine x minus x. We can do this without starting a new topic. That's what I mean. We have existing skills. We just need the primitive of this, right? So y equals. Now, what's the in the primitive of sine? That's negative cos x, and then minus half x squared. And we know, or at least have the habit that we put plus c. And so that is done, all right? So I'm just going to note here the solution to a differential equation is a function. Okay, and then I'm just going to cross that last bit out because what we have here, because of the plus c, the solution to a differential equation is a family of functions. All right, solution to a differential equation is a family of functions. Now, we are accustomed to them varying by a constant, but that is not always the case. So we have to be careful here. It could be quite a distinctive, quite a distinctive family of functions. Okay, so question 3. Oh, and of course, if we have more information, like an initial value or any value, if we know something like x equals 4, y equals 7, if those two values go together, then we can find c and we can make it a specific function instead of a family of functions. Right, moving right along. So solving these ones, y dash equals y. It says here that we're using inspection rather than technique. We had a technique to solve this one, but we don't have a technique to solve this one. All we can do is look at it and think, oh yeah, I know the answer. So what this is telling a story. The derivative of a function is itself. And we've heard that before in the context of exponentials. So if we have y equals e to the x, and then out of habit we'll put in plus c. But now I'm just going to put a question mark there. Is plus c correct? And the answer is no, because, sorry about my poor writing, because then y dash does not equal y. Let's just have a look at that. If y equals e to the x plus c, then y dash equals e to the x, but that's not equal to e to the x plus c. Okay, so we can't do the plus c. So I'll say therefore y equals e to the x. But that's actually not all there is to it. So we could have, or y equals 2e to the x. Okay, the derivative of that is 2e to the x, or y equals 17e to the x, or negative 17e to the x. So in short, we have y equals some constant a e to the x. Okay, and yeah, the a could be positive or negative. For question B, y dash equals 7y, then well, we've got y equals e to the 7x will fit the bill. We know better than to put a plus c, so y equals e to the 7x. And if we check, right, then y dash, if we, the 7 comes out, 7e to the 7x, and that is 7y. Okay, so that's a tick. And so once again, we can have any constant in front of here. So we'll have y equals a e to the 7x. And I'll leave that to you if you want to check that more formally. All right, so we've got an aside here. I should use a highlighter, not an eraser. All right, an aside. Trivial solution. What are we talking about here? Well, if I just sort of give myself some room here. There we go. So another way to solve this is simply to say y equals 0. And I don't really mean 0 the number, I mean 0 the function. So there's no x in here, so it just means that y is constantly 0. Now, if you look at that, well, the left-hand side is y dash, and the derivative of that is 0. And the right-hand side is y, and that's 0. So the left-hand side equals the right-hand side. So this is a trivial solution to this equation, and it works for this one as well. Or can be called a constant solution. So it's a trivial solution that doesn't really capture the essence of the of the differential equation. Okay, question 4. Another existing skill we can bring is to check that one thing satisfies another. So if I were to ask you to solve y dash equals 1 plus y squared, that'd be a tough ask. Maybe with some techniques later we could do it, but for now, it seems a bit difficult, and even by inspection could be a bit difficult. But luckily, we're given the answer here, and we just have to show that it satisfies it. So basically, when we show that, I'll go for the left-hand side, right-hand side working. So left-hand side in this is y dash, and y dash, if y is tan x, then y dash is sec squared x. Can't simplify that anymore, so the right-hand side is 1 plus y squared, and that's 1 plus tan squared x, and we know that that is sec squared x. So the left-hand side equals the right-hand side. All right, so y equals tan x satisfies, what happened there? Satisfies this differential equation. Excellent. Now, what about this one? Oh, and I should say, we don't know if that's the only solution to that, but it's a solution to that differential equation. Question B, verify that x squared y double dash minus 2x y dash plus 2y equals 6, so very complicated, is satisfied by this value of this function y. Well, we have a first and second derivative in this. That makes it a second order, more on this later, but a second order differential equation, whereas something like this, the ones we've seen so far, is a first order because it only involves the first derivative. So that's pretty simple. Second order can involve the second derivative only, or the second derivative and the first derivative and the function, but the highest derivative that it involves is the second derivative. Okay, verify this. Well, we need right, so because this is an existing skill, you should pause the video and attempt this before I do. All right, so left-hand side of what we're verifying is x squared times y double dash, which is 2, minus 2x times y dash, 2x minus 2, plus 2y, 2 lots of x squared minus 2x plus 3. And that is simplifying and expanding and so on now, so 4x squared plus 4x plus 2x squared. Okay, and I don't love crossing things out in working. I think it's a bit messy, but we can see that these three terms cancel out, and then the 4x and the negative 4x also do. So that leaves, equals 6 as required, okay? We're supposed to show that it equals 6. All right, question 5, I'm leaving till the next video. It's not necessary for you to get started on the exercise. The exercise does involve questions like what you've seen so far. And then the last one that we'll do for now, question 6a, solve y dash equals 2x given 2, 7 lies on the curve. This goes all the way back to chapter 5, primitive function. All right, so, but we are solving a differential equation. All right, it's saying find me a function whose derivative is 2x and it goes through the point 2, 7. All right, so well, we get very quickly, we get y equals x squared plus c, and then we substitute 2, 7, which gives us 7 equals 2 squared plus c. Right, that's 4 plus c, so c equals 3. Right, so therefore y equals x squared plus 3. All right, so that solves y dash equals 2x given 2, 7. Okay, I'm not saying you have to write that as part of your solution, I'm just reiterating what we've done. All right, so question 6, question 6a is done. You can do some exercise now. Question 6b is not so different, but it's got a few technical things that I want to spend a little bit of time demonstrating, and I don't want that to get in the way of you practicing what we've done so far. So do some work, and I'll see you in the next video.